So welcome back to the second half, your 7th lecture, where we deal with probability model. I just want to show you something real quick here that, remember I told you that some distribution is a special case of the other. Well, this is gamma distribution, but when k is equal to 1, it's the same thing as exponential. So if instead of doing this, I type in exponential, oops, exponential distribution, say 1.23 or whatever. Okay. Okay. This is what I get. Same thing. If I, instead of typing exponential distribution 1.23, I type in gamma distribution 1,1.23. I get exactly the same thing. Okay. Now, of course, if instead of 1, I make it k, and I vary, then I will get different shape. Yeah. So that's basically this page in Wikipedia, right? So when you go to see, that's k is equal to 1, k greater than 1. Okay, this is kind of static display, but this is kind of interactive display. Okay, fine. Right. Now, so probability model, okay, if you fit it against the data, that means you're given a data set. Now, I want to do something else, which is called random number generation. Okay, random number generation is like me making up a data set. Okay, now why would that be any kind of useful? Let's go to random number generation, Yeah, generating random variable. Okay, right. So this is like me playing God, right? I make an assumption. I say my distribution, okay, is equal to Poisson and 10. Poisson distribution. Okay. And say 3. Okay. So what's going to happen is that's my declaration. Okay. Now, this, once I have this, can I do that? Yes. Okay. This is like when you open up the Wikipedia page and you look up lambda is equal to 3, the mean is equal to 3. Okay. So basically that's, okay. So this distribution, Poisson distribution, right? So that's the lambda. When lambda is equal to 1, the mean is 1. Lambda is equal to 4, the mean is 4. Lambda is equal to 10, the mean is 10. How do you know that? There it is. The mean is equal to lambda. Okay, so no surprise there. So in this case, I make a case that my Poisson is this, right? Now, obviously, I know what the distribution looks like because I created it, right? So let's do this PDF of my distribution as a function of x there, right? Lambda to the x, e to the minus lambda, x factorial, x greater than or equal to 0. Otherwise, 0. Okay, that's what this means, right? So, in other words, if I Poisson distribution lambda, okay, it's going to be this, right? Fine. So I can always plot this discrete plot. X from what? 0 to 10. Okay. Actually, it goes up to infinity, but I'm just going to plot to 10. Can you guys see that? Right? So I'm plotting the PDF of my Poisson. that Poisson has parameter 3. So average, this is actually the mean of that distribution. If I put a wedge here, it's not going to fall. Okay, fine. Right? Now, what's random number generation? Imagine that I want to make up the data set whose histogram looks like this. That's what I mean by random number generation. Okay, how would I do that? Well, remember the little x is called random variate. So there it is. My generate data equal to random variate. Okay, what's my distribution? My distribution, how many do I want? Let's say I want 100. There it is, right? So again, let's say lambda is daily number of accident. How many accident can you have? Well, you can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, right? But if lambda is equal to 3, then the average would be 3. So this would be my random generate. So if I do this again, I'm going to get a different number. Okay. Now, let's do this. Let's put histogram around it. See? That's my histogram. So let's make it 1,000, right? So this is going to look a little bit like this. Can you see that? Okay. So this is the relationship. Okay, let me draw that again. Okay, let's put this on the same line. Okay. This is what we're talking about. Okay. On the left-hand side is a probability model. Okay. If I knew what the reality is from now on, for the next whatever days, every day we can have about 3 accidents on average. Okay, but it could be 0, 1, 2, it could be 100. Okay, and I say, you know, I'm God, I'm creating this world. Okay, the probability that there'll be an accident, X number of accidents over any given day is Poisson lambda equal to 3. What I did was I created this probability. You see that? There's a probability of no accident. There's a probability of 1 accident, probability of 2 accident, probability of 3 accident, 4, 5, 6, 7, 8, 9, 10, up to infinity. Okay? That's probability model. Okay? When you model the data, it's like you're trying to find the left-hand side. You don't know what lambda is because God didn't tell you what lambda is. Okay? But the situation looks like Poisson distribution. Poisson lambda. I don't know what lambda is. I look at the data, which is the right-hand side, and I estimate lambda is equal to 3. The random variate is the original case where I started with assumption lambda equal to 3. What would the data look like? Okay, so this is called random number generation, meaning you know the probability distribution, you generate number whose histogram will look like what you started with. Okay, you do this as if it's a game, and that's what I do. I do this, I generate this random number, I give it to student has to do something with it. In reality, what you are given is the actual number, i.e., like the histogram on the right-hand side, and you work backward to find out what lambda is. Does that make sense? Now, let me be very quick, and let me just tell you this. The whole of statistics, okay, which is a third part, it's a big deal, by the way. You can take a whole year of it and Ph.D. in it, but works like this. I have a data. based on what I understand about how this data came about, I know what support it is. Finite, countable, bounded, semi-bounded, unbounded. Based on what I know about data, I choose the family or the brand name. Okay, you saw that brand name from Wikipedia page, right? I choose from one. That's what professionals do. But you guys don't have to choose because you only have one choice, right? But once you have chosen that, you still have free parameter to fit. This is what fitting data is all about. I have histogram on the right side. I have histogram from data. Let's assume this is, pretend this is real data. This is my histogram. I have chosen Poisson. I am going to choose lambda that best fit the data. That's called data fit. That problem is because what you're estimating is lambda, and lambda is the parameter of the distribution. What you're doing is called parametric estimation. Okay, so parametric estimation. Now, this random variant is the opposite. Okay, in data analytics, most of the time you don't do this. You do this in situation where you want to model dynamic behavior. What do I mean by that? If I just collect data and try to fit it, that's what this is, right? Now imagine you have a system of interaction. Let's say this is the number of accidents. This number of accidents, right? And you're running a hospital, emergency hospital, and you have some kind of staffing plan, like you have so many nurses or whatever, right? And each of them also has some kind of randomness with ability to service patient. And maybe you have something else. You don't just have a number of accident or number of patient, but you have the distribution over the time it takes to service, right? So for example, instead of saying that tomorrow we have 3 accidents, we say tomorrow we have 3 patients. And then that each patient has a random amount of time, maybe an hour, 2 hours, 3 hours, right? So you have so many distribution, you have so many probability thing going on, and you want to simulate what would happen. So if I have this many patients, each patient has varying number of disease or number of hours, and I have 3 staff. How long would wait? How long would average waiting would be, right? Because a nurse can only service 1 person at a time, for example. So this would be this thing called, and I give you just the word for it, and I'll skip. I won't mention it again. It's called system modeling. Okay, so system modeling uses probability model in the opposite way we would use. Data analytics tend to be fitting the probability model to the data. System modeler would be something like, I know what the probability distribution is, but I don't know how they interact because there's random this, random that, random this, random that. I want to simulate what would this chaotic world look like, right? And then I would measure some kind of performance statistics. Now, this is done in real life, by the way, guys. For example, if I'm running a bank branch, I can then say, oh, how many customers arrive? How long does it take to service? And if I have 3 staff, 3 bank teller versus 2 bank teller, is it going to be a long queue or not? Okay. In logistics, if you have a friend in logistics, this fall under the whole thing called queuing theory, literally. Okay. And this is important. Why? Because you can optimize this. If you have a lot of bank teller, people don't wait, but it costs more, right? If you only have 1 bank teller and you have a long queue, what happened? They go to a different bank. Okay, so this is what system modeler do. System modeler use probability model for that kind of purpose. Okay, but for ourselves, we kind of like the other way around. We look at the data and try to fit the distribution, right? Now, statistic people would do this. First, they would estimate. That's one problem. It's called parametric estimation. Okay, this is actually part 3 of the chapter, but I can just give you a hand waving right now. Parametric estimation, meaning I've decided I'm going to use Poisson distribution. What's lambda? Or I've decided based on this data, it's going to use gamma. What are the 2 parameters? So that's how I fit. So parametric estimate the parameter that best fit the data. Okay. Now, in statistics, most of the time, they do that estimation, but they also do the other problem. That problem is called hypothesis testing. Think of it this way. If, okay, and I'm just giving you a hand-waving situation. If you have a regulation, okay, that pollutant that you release into the river can be bigger than whatever, 7 parts per million. Okay, 7 parts per million. Okay, that's a regulation. Now, a factory operates and release pollutant. And the factory is supposed to, on average, release no more than 77 parts per million, right? But it's a random process, isn't it? So is it possible? Is it possible that on the day that the inspector arrives, it's so unlucky that when he measures the concentration of pollutant in the river outside the factory door, it is 7.1. Right? Is it possible? Yes. Is it likely? I don't know. Well, certainly, if you claim to pollute less than 7 parts per million, and I measure and I get 6, I'm happy. If I get 7.1, right? Should I give you the benefit of a doubt? If I measure and instead of getting 7.1, I get 200. Am I going to give you the benefit of a doubt? No, right? So a lot of the problem is not estimation. It's testing the claim value of the parameter. Let me say that again. Okay, let me say that again. So probability means you have a bunch of functions that stand ready in the Wikipedia page. You can select any of them to fit the data. Based on your data, based on support, you have 5 types of probability distribution function. You choose one from each type or use a few to try, but you know, in your case, you only choose one. And then you have the parameter value that has to fit the data. You estimate which parameter best fit. Okay, so basically you try to draw the line of the PDF that best fit the histogram. That's what it comes down to. But professional statisticians have a different job. They tend to be kind of like the situation I described. The job of a regulator is not to estimate how much pollutant the factory releases. The job of the regulator is to see whether or not that sample on that day, on that couple of days, is consistent with the claim that the factory produces pollutant less than 7 parts per million. Okay, so it's a more robust way of answering because after all, it can be any value, right? The mean can be 7.9, sorry, can be 6.9, 6.8, right? Anything below than 7 is good. But even if it has on average pollutant less than 7 parts per million, you can have very bad day. Occasionally, right? Average is less than 7, but on that day that the inspector arrives, right, catches it at 7.1. Okay. Now, obviously, in reality, the regulator is not going to arrive and take 1 measurement. He's going to take 3 measurements. He's going to take 4 measurements. Now, if he takes 10 measurements and the average is still 7.1, it's a little bit harder to argue, right? Right? In fact, the more sample it is, the more the sharper the conclusion can be. So that if I take an average of 10 days, maybe the average come up to 7.01, I would be okay. But 7.1, no, you're doing something wrong. You're doing something wrong. Okay, right? So this kind of like checking, this kind of hypothesis testing is what professional statisticians do. Okay, we are dealing with data analytics. Yes, there are occasions when the data would fit those distribution, but as you will see when we come up after the break, we definitely statistical distribution is very small part of what we do. Okay, so okay, so generative. So let me show you, go back. So this generating random variable, this example that I made up. Okay, if I generated 100, the histogram will actually not look very good. Just like you have to choose the right. Just like you should have the right parameter to fit the data, right? If you generate a few sample, you probably won't get the histogram that looks like what you start with. This is my truth. Okay, I want to generate random number that looks like this, but if I generate only 100, you can see that it's not very good. If I generate 1,000, it looks closer. 10,000, it looks better. So the more I generate, the better it looks. Okay. Bernoulli, binomial, all works the same thing. Now this is where, by the way, you go to a library. So I gave not only binomial, I gave negative binomial, I gave a few other things. Okay, so this is kind of catalog. This is the beta. It's beta 1. Okay, so these are all. This section here is about cataloging that I show you by hand earlier, right? Chi-square. Chi-square is another one. Log normal is another one. But anyway, I gave you 5 names. Okay, I gave you 5 names. As a homework, I want you to read all of this. Okay, all of this. And if anything, all you need to do is just memorize a few things like, is log normal? What is the support of a log normal distribution? Actually, log normal has the same support as gamma distribution. Okay, that's all you need to tell me. Okay, unbounded. So again, in Wikipedia page you have 100. In the textbook you have like 10. Okay, and this class I gave you like 5. Okay, now before we so that's what happened. It's about distribution of X, right? Randomness. Okay, so the whole thing is about random event that translate into number. We call it random variable, right? The thing itself, that's random, that's nature, not the number. The number is always 1 for every head you see, 0 for every coin you see. Okay. So the next thing is 2.4, multivariate probability distribution. Now, this is very important. Why? Why? In probability and statistics, if I want to know the distribution of height, that's it. That's the end of the story. If I want to know the distribution of pollutant, that's the end of the story, right? But most of the time in statistics and also in data analytics, it's not individual X that you care about. It is X and Y. Okay. So let me say first, X is random. Y is random. X and Y individually are random. But, is it possible that their randomness are not completely independent? In other words, if you know that Y is random, and you know that X is random, So X can be anything. Okay, the mean is here, standard deviation. So 68% between mu plus minus sigma. Fine. Same with Y. However, if I give you more information and I say X and Y are positively correlated, and X right now, this X is bigger than average. Would you guess that Y is also bigger than average? For example, let's say, I don't know if this is true in science or not, but let's say higher humidity, or let's say lower barometric pressure, right? Okay, this is bad science, but lower atmospheric pressure correlates with higher probability of rain. Correlate. Today, the barometric pressure is, was it higher or low? Lower than average. So the chance of rain should be higher than average. Both random. Okay? You see what I mean? So X is random, Y is random. But if you know that X and Y are positively correlated, and X is higher than its normal average, Y should be higher than its normal average. If X and Y is inversely correlated, the day that X is higher than average, chances are Y is also less than average. So information about Y is given by X. Okay, so let me go to I'm making some example up, okay? So if this is distribution of X, this is distribution of Y, okay? Right? What's the probability X is between here and here? Okay, well, that's 68%. Okay? So right now, you don't know anything, right? You just, this is your model. You collect data for X, you collect data for Y, and then you fit a normal distribution, and this is what you get. Right? So that's it. That's your uncertainty. Now, let me do the opposite. Let me do something else. What if that histogram is in two-dimension histogram? And the histogram, can you imagine it's like this? It's like a turtle shell, such that if you look on top, it looks a bit like this. Okay? Looks a bit like this. Okay? Now, normally, okay, look at my hand. Okay, this is what you have, right? So normally you have X like that, Y like that. I gave you extra piece of information. X and Y tend to be positively correlated. You used to know that 68% of the time, Y is sort of like between here and here. Okay, so this is mu plus minus sigma for Y. Okay, right? Can you see that? Let me draw the whole thing over. Okay. 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 Right now, I don't know any better. So X has its own, 66 mu plus sigma minus sigma is kind of here, right? Same with Y. Y has its own mu plus minus. So right now it's like this. Okay. right? Because X is positively correlated with Y. And I give you that today, just today, X is higher than its mean. X is over here. What happened now? Now, first of all, this is the data you collect. So you have this 3D histogram. We talk about it in visualization, right? Likewise, you can have normal that is bivariate normal. So it looks like this for X, it looks like this for Y, and on top, it looks like a turtle, right? So that's what you fit. So you fit this already. And somebody just whisper in your ear that today, X is higher than its mean. What happened? Once you know what X is X a random variable anymore? No, it's an actual value, right? So what happened is you make this intersection, right? All of a sudden, that plus or minus mu shifted, right? So basically, you kind of rescale your expectation, okay? Because now you know, right? It used to be you used to think that X and Y can be anywhere. Y can be anywhere between here. But now that somebody whisper in your ear that X is higher than average today, then the new thing that you draw would look a bit like this. You have less uncertainty. You have more information. You kind of like get, and this is common sense, guy, right? This is common sense. Now, this is when X and Y are both random. That's why we call this multivariate normal. Okay. Now, let me draw you another example. Okay, you remember this thing, right? Okay, X has this distribution, Y has this distribution. What does this remind you of? It's not the same as what you saw in high school. What you saw in high school is different. What you saw in high school is a regression equation. X here is not random. Okay, X here is not random. Y here is random around X. Now, this is a picture you see more often, right? Right? Okay. But can you see that it's a similar kind of logic? Okay. Except, you know, in the case I drew before just now, both X and Y are random. In this case, Y is random given X. X is something that you can control. So you can think of it as Y is like a temperature. And X is like how much of a knob you turn. Because even though you turn it up, it doesn't go all exactly up. It's sort of like that, right? So X is something you can control precisely. But even if you control X precisely, there's some uncertainty about Y. Because just because I set the heat to high, that doesn't mean it goes to exactly the same degree. Okay, let's say this is an old-fashioned air conditioner. Okay, so I turn the voltage up, it's a bit louder, or I turn the air conditioning higher, it gets cooler, but it's not precisely 27 or 23 degree. It could be plus or minus. So this is what's called regression. In this case, there's only one randomness. So I don't want you to confuse regression analysis with multivariate distribution. Okay? Does that make sense? Now, where are we going with this? I like saying this, and you probably should be sick of me saying this. There's only two questions that we ask. Where are the X? Right? And the other one is, how does this relate to Y? Okay? Where are the X's? Means I don't know. There's something random about X that I need to find out, right? Well, In multivariate distribution, both x and y are random. So essentially y in that case is just x2. Okay, so this here, x can be any dimension. If x is one dimension, it looks like this. Okay, or whatever. If x is two dimension, then it kind of looks like this or whatever. Looks like a block kind of thing. Okay. Actually, it looks, if it's two dimension, it maybe look like this, and then y would look kind of, right? Okay. So that's where are the x's. And so when I talk about multivariate normal, then I'm talking about this guy. But this is different. This is like, if I knew what x is, what's y on average? So at the end of the day, it always comes down to this. You want to know where your data is, and you want to know how can you predict something else from something else. Okay. Finally, just to confuse you guys, you know what an autoregressive model is? It's predicting y from x, except x and y are the same thing, just different time. Okay. So if I predict height from weight, okay, weight is, say I can say I'm just going to look at the guy who's 70 kilograms and predict how tall that person is. So y is height, x is weight. Okay. However, if I'm talking about predicting the weight of the person tomorrow or 1 month's time, given I know the weight of this person today, that's called autoregressive. In other words, x is x today, yesterday, the day before, y is x tomorrow. Okay. So that's basic. That's why this picture works. Okay. This picture works. You want to know where is x. Except when I talk about x, I could be talking about x1 and x2. Okay, just so long as you know that. X given what y, as long as you know that sometime y is equal to xt plus 1, and then x is equal to xt and xt minus 1 and so forth. Okay, as long as you know this includes. Okay, but that's it. That's it. Okay, that's what data analytics is always going to be about. The difference is today, if x is univariate, you have 1, 2, 3, 4, 5 different functions to model it. Okay. If x is bivariate, how many multivariate distribution do you know? Actually, you only know one. Multivariate normal. Doesn't look fair, does it? Doesn't look fair. Well, that's life. I'll tell you why. Okay, so once again, if you talk about this randomness in X, you can have discrete, countable, bounded, semi-bounded, unbounded, right? And unbounded, you have normal distribution. So I'm talking about X and Y being jointly random with some kind of correlation, meaning that higher than one means higher than the other. In theory, wouldn't you rather have something like multivariate binomial? Wouldn't you have, let's say bivariate, just two variable, okay? You would like bivariate binomial? Wouldn't you like bivariate Poisson? Wouldn't you like bivariate gamma? Wouldn't you like bivariate beta? You would, but in reality, you only taught bivariate normal. Okay. Just say, you're sad. Okay, that's all you learn. Okay, that's all you learn. That's all you learn. However, I can tell you, but because this is not a deep statistics class, but any of you who want to do this as a project, okay, as a project, you can talk to me. For one thing, there is multivariate version of binomial. It's called multinomial, obviously. For everything else, there is no generic version. There's no multivariate Poisson. There isn't. However, you can, and this is something that is very hard to describe, you can have two Poisson variable that is correlated, except that correlation has to be borrowed from multivariate distribution. Does that make sense? I hate to do this to you, but okay. Okay. Watch me. Watch my hand. You have binomial. I'm going to draw this. Okay. You have Poisson. You have beta. You have gamma, and you have normal. Okay. You can study all this, right? And in the book, there's a few more. Okay. So instead of this, there's like a log normal. Okay, fine. For bivariate, okay, bivariate, which can be generalized to multivariate, you only have this thing. And in mathematics, it's called binormal distribution. Okay, bivariate normal, so binormal. Yeah. Okay. Question is, why don't you have multivariate or bivariate? So you also have multivariate normal, by the way. Okay. So this is 1 dimension, 2 dimension, 3 dimension, whatever. Okay, you can do that, right? Let me just tell you that that's how life is. Because they don't have a lot of this. Okay. However, should you be sad? No. There's this thing, I'm just going to give you the name, okay? This thing where X is normal and Y is normal, together, that togetherness, that correlation model, that the way you put X and Y together, technically is known as a copular function. So in other words, there is Gaussian copula. So in other words, if X is normal, Y is normal, you add them together using this thing called Gaussian copula, you will have bivariate normal. Okay. Now, normally nobody studied this way because in statistics, you just go to bivariate normal. The point is that this element, this copula, is a way of modeling general correlation between two random variables, 2 or more. So you can have copula, this Gaussian copula, to join 2 Poisson. You can have Gaussian copula that join 3 Poisson. Actually, to be honest with you, and you can have Gaussian copula that join Poisson with beta. It's very general. This is called copula statistics. And that's what professional statisticians study as well. It's a little bit beyond us, okay? Just you know that it exists. What I mean is that if you have data and you have multivariate data and you know that not all of them are normal, if they're all normal, you can join them using Gaussian copula, basically use multivariate normal. But if you have multivariate and you want to model together as a joint distribution, and you know that not all of them are normal, you have to join them together using this thing called copula. You don't have the technology for it, but you can ask your friend for it. And it's built in Mathematica. Okay. So it's called copula distribution. Okay. Now, this is a bit tricky, more than you need. Why? Because first of all, we are doing data statistics in a more general case that doesn't have nice distribution. So forget about copula, normal distribution, bivariate normal distribution. We are going to be more likely interested in multivariate data that doesn't have any kind of distribution. Okay? And you're trying to sort of like picture what it looks like. So it's not going to look like this big turtle. Okay? Imagine you have X and Y, and you look on top, it looks like a banana. Right? Any kind of shape. And that's where machine learning comes in. Machine learning is more generous. Okay. So it doesn't say to model this data, choose from Wikipedia list. Okay. And you have even smaller lists. You have a list of 10, and today you only learn 5. Okay. So those are very restrictive. Okay. So even if mathematicians over 300 years have come up with 300 distribution, it's still just 300 distribution, 400 distribution, fine. But chances are you're not going to find any kind of distribution that fits a banana looking data set. Okay. So real world data can be really, 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 really messy. And that's why even though you have learned up to now multivariate, normal, you can learn Gaussian, beta, and it's got mathematical definitions, very nice. In real life, sometimes you have to let that go because you can't use traditional parametric statistics. Okay. So let me give you a word. Because statistics, probability model that we studied so far has function and has parameter. Sometimes these are called parametric method. So when you do things like neural network, clustering, all kind of machine learning stuff that we do after the midterm exam, those sometimes are called semi-parametric or non-parametric method. Okay, so far your life is parametric method, so it's kind of nice. Does that make sense? Okay, you're studying real data. That real data, if it happens to come out of a process, for example, like random coin toss, yeah, everybody has the same P. By the way, multinomial is not multivariate extension of normal binomial distribution. That was an erroneous mistake. Multinomial is something else. Yeah. Yeah. Anyway, so it is a generalization of binomial, but maybe not the sense I meant. So just ignore what I said earlier. You have to edit that thing out. Okay. So right now, just tell yourself that you now understand what professional statisticians do. Most of the time, they deal with, say, univariate distribution. A lot of time, they deal with multivariate distribution. Sometimes they deal with regression equation, which means predict y given x. But in all of these cases, you are confined to making a lot of assumptions. For example, this kind of bell curve, right? Or this kind of stick shape, or this kind of skew shape. So there is a limitation of what the shape look like because these are defined by well-established mathematical formula. Okay. So now imagine when situation is messy, how would you deal with that? Okay. Now, when you go to machine learning, you're going to learn about techniques that basically just fit anything. But also, before you go that, you can think of, well, what if I use one normal distribution and I add another normal distribution? I start to get funny shape, right? So even from basic statistics, if you start to use them in combination, okay? So again, all this is restrictive. All this is restrictive. Okay. If I want to fit a distribution that looks like this, okay, you can. Or can you? There are some intermediate steps. For example, hey, let's imagine that this is equal to this plus this. Can you do that? Can you do that? So there isn't a distribution function that looks like this. But hey, you can draw normal distribution, right? And you can draw another normal distribution, right? And the area of the distribution has to go to what? Has to be 1, right? So what do? How about I take this normal distribution and multiply by 2/3, and this distribution multiplied by 1/3, add them together. What's going to happen? I'm going to get the distribution that has area of 1. Okay. These are semi-parametric. This is a little bit fancier way of doing statistics. Okay. Now, statisticians don't like this, but it's a cheat code basically, right? It's a cheat code. Because normally what happens is they say, oh, this data is not normal. I'm not going to deal with it. So you think of statistician as very precise, but very snobbish analyst. Oh, this data doesn't conform to my notion of normal distribution. I'm not going to touch it. It's a dirty data. Okay. So if imagine that you're not so snobbish, right? But you want to use traditional statistic too. How would you do that? Okay. Before you go to neural network all the way, you can do this. You can do something like, let's take half a normal. So this thing is 2/3 normal, 6, 7, and 1/3 normal, 12, and 4. Okay, you can do that. And that's called mixture distribution. That's also in mathematics, I think. Okay. Now, so there are way of trying to make statistics deal with real world data. But of course, when we come back after the break, we'll go to unsupervised learning. That's when you really deal with real world data. You say, okay, I really don't know if it's normal distribution, gamma, mixer. It's just kind of banana looking shape, right? Okay, that's when we come back. But let's spend a few minutes talk about the midterm exam, right? So the midterm exam is going to be open book. You are going to be asked to create a lot of manipulating. So for example, you can have a data set, and basically your answer would be something like, I create a manipulate visualization. So it's manipulate. Okay, so you have some kind of data, and this may be from example data, and then you have to do some kind of plot, and you have to sort of like okay. So scaling, distribution, all kind of stuff, generating random variable. So anything up to chapter, chapter today was 5, 4, 2, 4. Okay. So because it's an open book, it's gonna be more difficult, obviously, right? You can look at examples. So I will ask anything from, let me just make this easy. Let me put them into groups. Okay. So there's data concept. All right. So this is basically chapter 1, right? Concept of data, data point, data set. Why do I call it data? Why do I call it information? All kind of stuff. So data concept, this is kind of like conceptual. Mathematica, primitive. That's basically, chapter 2. So create a list. Why? Because it's not a programming class, but certainly, to have the tool, it doesn't matter what tool it is, you have to know the primitives. Okay, creating list, creating table, plotting, okay, applying function, defining function. So I say, please define your own function that takes X and Y and do this to it or something, okay? Now, you're gonna have to, definitely a lot of list manipulation. Also, I put emphasis on module, right? The idea that you create a local variable, I think that's important to me. A lot of people don't think that's important, but I think it's good practice. So the primitives, right? And then you go to interactive. So you use manipulate basically, right? And then the concept that's linked to more probability. So that's when they say, oh, well, you know what? I think that the number of accidents on a given day is Poisson with lambda equal to 3 cases a day. What's the probability that tomorrow you have between 7 and 9 patients? Okay, so you need to use that quickly, right? Okay, so that's quickly. There are other ways to say that, but this quickly is the one that's shorthand for everything. Okay, so that's kind of right. So and PDF, CDF, know that, and a little bit of memorization exercise, which is that those name probability distribution name that I gave in the book that I didn't mention today, for example, in this situation, you could use gamma. In this situation, you can use beta, and you have a log normal. What kind of situation would you use? Same as log beta or same as gamma? You just have to know where they are, basically. Okay, right? So again, if you can memorize these 10 in the book, your life is good. You don't have to have the 300 in the statistic book. You don't have the 50 in the Wikipedia page. Okay, but those are, again, just that. Okay. Now, I'm going to give you a little bit of a challenge. I'm going to ask that kind of question about probability and statistics, but instead of asking what's the probability of X being between 5 and 7 given its Poisson, I'm going to do at least one that is multivariate. And because you don't know any multivariate distribution beside binomial distribution, okay, there'll be one on binomial distribution. Okay, and the idea is just type in binomial and shift enter, right? And that tells you how to enter the mean of X1, mean of X2, correlation, right? And the opposite side of probability is a random variable generation, right? So I asked you to maybe I'll generate some random variant. Okay. Maybe I'll even ask you to generate data that is good for linear regression. What would that look like? Well, that's like saying y is equal to f of x plus noise. What's the noise? Normal, right? Okay. But again, a lot of it will be a complete. I was thinking the other day of doing something like, how about if I just do a manipulate screen and do a screenshot and ask you to replicate that? But that could be a little bit mean. But basically, manipulate, module, function definition, list, table. These are all the primitives you'll be using. Okay. And today you use a lot of probability distribution. Copula, I'm not going to cover that. That's a little bit, but if you're interested in your data set, so you might be sitting on medical data set that just from looking at a histogram is not normal, but you have a few of them that are jointly distributed. That's a copula project. Okay, so we can talk about that in detail, but I don't think I'm going to ask you copula question in the exam. That's a little bit hard. Okay, but know that there is mathematically you will not find something like multivariate beta, multivariate gamma. Those are not, they don't exist. Basically, you have to Lego yourself. Okay, just add distribution, what's called marginal. Individual random variables called marginal distribution, and then joint distribution is when you add the marginal and the copula together. Okay. So once you have that concept down, yeah, you can work with. And when we come back, remind me, just before we go to machine learning, I want to give an exercise. Actually, I can just remember I told you that if I assume that this data should have, right, should have, say, Poisson distribution, find the lambda that best fit, right? So that's kind of like parametric estimation. Try to look that up, okay? And finally, there's like a magic function in Mathematica called find distribution. This is like saying you have no idea. You don't even know if discrete, it's continuous. You don't care. You just give this data set. This is a sheet. You shouldn't do this in real life. But I do it to get an idea. Find distribution. That's also a function in Mathematica. And it's a cheat code because Mathematica is just going to search over a few choices. And it's going to come up with you with not only the name of the distribution, but the actual parameter value. So it would be like you give the whole data set, all right? And say, find distribution of this, and Mathematica returns gamma 1.2, 3.4. You don't even have to choose the name, and so that's a little bit of a cheat. But maybe I'll ask that as a bonus because it's very handy. Okay, it's very handy before when you get. I come up with some data set that's not normal all the time. Okay, and sometimes I want to get an idea, and they will come up with some really strange distribution that you never heard of. Benzo, I don't know. Okay, so maybe I'll ask a little bit of bonus about parametric estimation and find distribution. Those are like cheat code. Okay, you don't have that in Python. You have to specify, so you can't say find me anything. Okay, except some library might.